Dear participant, good morning and welcome to this new series of the lecture Mathematical Computing with Python, Calculus Made Easy with SymPy. So, computing tools play a very important role for the computing, and we have several softwares in the market like MATLAB, Mathematica, Maple, R, Python, SymPy, etc. So, like Python is free available and we can easily integrate for the scientific purpose. So, there is the most important library in Python, which is SymPy, Symbolic Python. Okay, Sim means symbolic mathematics and Py means Python, and combining these two, we have SymPy library. This script demonstrates how to perform symbolic calculus operations in the Python using SymPy library, which is an open source symbolic mathematical package. Now, by using this SymPy, we can define and manipulate algebraic expressions symbolically. We can perform differentiation and integration analytically. We can compute limit, series, expansion, and substitutions, solve algebraic and differentiation equations symbolically, visual and format results using pretty printing or the LaTeX. So these are some key topics which we are going to cover during this series. We are talking about the creating symbolic and mathematical expression, performing differentiation and integration, calculate limit and series expansion, solving equations, differential equations, simplify and factoring expressions. So these are the content which we are going to cover during this series. And for this we are required Python 3x and SymPy library install using pip install SymPy. Okay, but here we will use this Python library in Google Colab. Google Colab is again an free platform which provide an interface using Python, which is free available, and we are not required to install any software, but only the Gmail account is required. So I let you know how you can start. Here you can see I am taking one more account here, and then after we will discuss everything how we can use it. So here you can see this is my another Gmail account, and which is login. You will click here, you will type here Colab. Okay, so you can see here Colab notebook, or either you will enter Colab. On the top you can see here is the welcome to Colab link is there. So as soon as you will click on it, the link will this pop-up will open, and just you need to click on the new notebook. So before starting the SymPy, just I would like to have brief introduction, the environment of this Colab notebook. And this Colab notebook is completely based on Jupyter notebook. So the content which you will create at this place we can use in the Jupyter notebook, and at the end when we will cover all this content, I will let you know how this file you can use in Jupyter notebook also by installing offline software. Okay, so but now we are using only the Google Colab, and which is based on Jupyter notebook, and Jupyter notebook is again whole is written in Python. Okay, so Jupyter notebook is very supportive to use Python, and all the libraries we can easily use here. But one more thing I let you know, in Colab we have all the required libraries are already installed here. We are not required to install any library or the package. All the packages libraries are available here, just we need to import here. So this is the just we have the interface when you will open, and first you can give the untitled name. You suppose that here I am putting the symbolic mathematics. Okay, You can give any name according to your need. You can update the name. After that, you can see here the file. You can move, you can delete. So many options are there. You can download from this place. You can download the file. There are two options. First is Jupyter file extension, and second one is the Python. So if you want to use this file in Jupyter notebook, you can use this one, and for Python you can use select this one. Okay, and if you want to print in PDF, you can print from this place in PDF format. And here you can see we have the two options. One is code and the other is the text. So if you want to write any text, then click on this place and you can give the name or any text which you want. Suppose I want to give the title of this file. So what I will do, this is the title to write here. Okay, I give the name, and if you want to bold, then use double star on left and right. Okay, and you can see on the right hand side, this is now in bold. This is in bold. And if you want to increase the font size, then use here hash. So by using hash, the font size will increase. Okay, and when you will shift and enter, so this will print, and you can see if this is the title page, then this must be on the top. Okay, so these are the arrow sign. By using all these arrow sign, you can upward and downward the shell according to your need. If you want to again edit this file, double click on it and you can edit it. This is the title page. Okay, I give the name here, title of the page. Okay, and then shift and enter. So you will put your title at this place. And here the other things which are very important to discuss here, if you need to give some description, you can enter, and here you can put the description. Description uh, and if you want this part is bold, you can do. Okay, so you can add here description of the entire page. Okay, and so on. And here we are using the colon sign. So whatever you need, you can edit everything. You can prepare your file, document file, which will include the text, heading, subheading, equations, okay, as well as the code of the same. If you write, one part is more important to discuss here. If you have some mathematical expressions, or you want to write any equation here, so LaTeX, this Jupyter notebook is a LaTeX port. Okay, so syntax for any equation which you want to write here is in the LaTeX format is required. See here the quadratic equation. Here I am using this sign, ax square plus bx and plus c is equal to 0, and you can see that this is in the mathematical equation, ax square. Okay, and yes, so you can easily write here the mathematical equations. And sometimes if you are using double dollar, so this will do same as we are using in the LaTeX. So this equation will be separate from the text. Okay, but here we are not able to give the equation numbers, and I would like to check whether it is possible or not to give the equation number. Slash begin equation and then end equation, right? And equation. I am checking because I am doing first time. And here we have ax square plus bx plus c is equal to 0. Okay, and then shift and enter. Okay, you can see there is no mathematical equation number. Okay, only the equations will be entered. Okay, so either you are using this simple sign, or you can using the this format to write the equation. One of them we can use to insert the equation. Okay. So the other symbols which we are using for the integration, differentiation, etc., for symbolic expressions to write the equation or the function, we will use LaTeX. Shift and enter, and the coding part will be at this place. Okay, if you are interested to write any coding question, and hash sign is using for comment. Okay, this is comment. Okay, and suppose that I'm using addition. Okay, I'm taking here a is equal to 9, b is equal to 7, and c is equal to, I have a plus b. Okay, so a and b are the parameters where I have stored the values, and the values of a and b are 9 and 7 respectively. C is equal to a plus b. I choose here very simple addition operation, sum, and then we need to print these values. Okay, just what you will do, you will run this code. Okay, so when you will run this code, the output of this part will be in the next shell. You can see here in the beginning it will take a few seconds, and after that because the statements or the shell which you are using must be connected for the cloud computing. And here now you can see this part, here is right green sign. Okay, and now connected to the Python 3 Google Compute Engine backend. And you can see here the RAM size is available 12.67 GB, and disk size is 107.72 GB, and we are using only 1.05 GB for RAM, and for the disk we are using 39.27. Okay, so this is free available, and we can use this space for our personal computing and to learn anything related to the Python. So now come to this file which I have prepared in the same way using as I demonstrate. So you can manipulate everything. Okay, and you need to edit, then double click on it, and you can edit all this. Okay, so the left part you can see this is editable, and right hand side is the output of this file. So shift and enter, this will be in this format. Now this is my affiliation. You can see Department of Physical and Mathematical Sciences, and Baba Farid College of Engineering and Technology. Okay, so what we do now, here are some important libraries which are required for our present computing. Very first library is the SymPy. Okay, SymPy is already exist in our Colab Jupyter notebook. Just we need to import. So when we use this statement, as you can see here, from SymPy import star. Okay, so this will import all the classes, function, symbolic symbols from the SymPy library. And for example, you can see symbol, equation, differentiation, integrate, sign, cos, etc. And it allows you to use the SymPy function directly without prefixing with the SymPy. Okay, so just directly we can use, and we will demonstrate various examples throughout the lecture. Initiate underscore printing enables pretty printing of mathematical expressions in the output. Display formulas in more readable and text book-like format. Okay, and these are the variables x, y, z, t is equal to symbols. X y, z, t whenever you are going to use some variables and symbols. So first we need to declare the variables. Okay, so here this statement is giving you we are going to define the variables x, y, z and t. These are the symbolic variables to write any equation or the expression, function, etc. Second, we have to declare the integers also if it is required. So for that, we are using here k, comma m, comma n is equal to symbols k, m, n. Okay, so there is a little bit difference from this place. K, x, y, z, t is equal to symbols x, comma x space y space z space t inside the quote sign. But for the integer, we are using integer is equal to, so this will define the k, m, n are the symbolic integers, integer value. Okay, and then f, g, h is equal to, we have calculus functions. Okay, so we need the integers, we need to declare the symbols for the variable and some functions symbol. Okay, so by using all these we can declare. So now after that we have very first example which we are going to talk about this place. Okay, so here we will take the derivative and partial derivative of the function. So in the very first example you can see f is equal to x square 2x cube plus 2x square plus 3x plus 5. So first we have to write this as expression is equal to, we have x cube. Remember that we have to execute all these statements which you can see. First you have to import this one, then you have to import and you can see here 3 dots are in orange color, but as soon as this will be connected, the 3 dots become now in green. Now this will import the library, then we can execute this one, declare the variable by clicking on it, and then you can declare the variable, then integers, then we have calculus functions. Okay, and now come to here, this is the equation function which we wanted to differentiate. So expression is equal to x cube. For exponent we have to use this double time, and this is the x cube. Okay, then plus 2. The syntax is very important, how we are converting the function or the equation in the Python syntax. Okay, so you must be see this syntax very carefully. X square, then we have 3x. Okay, 3 product x, then I have plus 5. Okay, and again write the expression, this will print the value. See here, when I will execute, you can see this will return the value in the next shell here. Yeah, this is the function which we store in the expression expr. Now for derivative, to take the first order derivative. Okay, take first order derivative. We can write here def underscore expression. This is nothing but and only the symbol. Okay, and will be equal to, diff is inside inbuilt function in the Python, where the library which we are using here, SymPy. Okay, so the diff is used for the derivative, whether it is a derivative or partial derivative, we will use diff function. Okay, and here we will pass the function which is expr. So the function is stored inside expression variable, and we want to differentiate with respect to x. So now when you will execute this part, this will take the derivative, and to print the value, use again diff underscore EPRS. Okay, actually this is the expression EXPR. Okay, EXPR, and this also expression EXPR, and now execute. So this will take the derivative, and we can see that 3x square plus 4x plus 3 is the derivative of the above expression. Now we can have the next one, which you can see here. F is equal to sin x cos x. Okay, so we will first we will write the function. And we are taking here expression is equal to sin x cos x, and then expression to print the value. So shift and enter. Okay, so you can see the function which is on the right hand side of f is equal to sin x cos x, we have stored at this place. Now we will take the first order derivative. Take the first order derivative. Okay, enter, and here we will write diff expression, and the function we have is cos x sin x. When you will execute, okay, you can see the derivative of this product we have is minus sin x square cos square. Okay, this is the derivative. And now we can see we can have the next example. Scroll down it. So here we can see f is equal to exponential x log x. Okay, so for that write the function. We are using here expression is equal to exp product log x. Okay, and when you will execute, this will return the value as you can see here, e raised to power x log x. And to take the derivative, we will use here expression, yes, expression comma x, and this will return the derivative of the function. So this is the derivative of this function which we write here. Next we have the higher order derivative, and for that first we have to write the function f equal to sin x, right? And here we are using the expression, okay, and sin x. So when you will execute, the function is here, this is the sin x function. Now if you want to take the derivative of this function, and we are talking here the derivative of higher order. Okay, so higher order derivative. Okay, so for that we have to write here the expression. Okay, so first I would like to show you, if you are using here x we are using here 2 times, it means this is the derivative of second order. If you are using single x here, this is the first order derivative. Derivative of sin is cos x. If you are using here x comma x, this is the second order. Okay. If you are entering one more x here, so this is the third order derivative. And third order derivative of this function we have is minus cos x. Okay. And the same we can get by using the numerical value 3. And you can see again the value is same, minus cos x. Okay. So whether you are using the numerical value or you are increasing the x order, the value will remain same. So this will easy to write the numerical order. If you need the 10th order derivative, okay, just enter the number. Whether you have to write x 10 times. Okay, so sometimes this may create some error, but here by using in this way, we can easily give the instruction to take the higher order derivative. So this will return the 10th order derivative. If you need the 100 times, just increase the number. Okay, and if you need the 1000, so this will the 1000 times derivative of a sine function. Okay, so in this way we can assign any order of the derivative of the given function. Along with the I have the example number 5, which is we are using for the partial derivative. Very interesting example. Suppose that we have the expression we are using here. First write the function in Python syntax. So here we will use expression. So expression we are using x square. This is the x square. Then product y cube plus sine x product y. Okay. So when you will execute this shell, this will return the same expression which you can see here at the place x square y cube plus sine xy. Okay. And then if we need the partial derivative with respect to x, what I will do? The expression xpr is equal to, I will use here exp, is equal to diff. Okay. And this will take the partial derivative of this expression with respect to x. See, so this is the derivative of this function with respect to x. 2x y cube plus the derivative of sine is cos xy, and again the derivative of xy with respect to x is y. If you are taking with respect to y, then we have 3x square y square plus x cos xy. So this is the partial derivative with respect to y. Suppose that I need partial derivative with respect to x and y both. Then I can write it as x comma y. So this is the mixed partial derivative. Partial derivative with respect to x as well as with respect to y. You can write the syntax in this way. If you need the partial derivative with respect to x is 2 times and you can write it as, and with respect to y 3 times. So this will return the value. We can have one more other way. We can write here exp underscore partial is equal to, you can write here derivative. You will write here the complete function. Okay. And then when you will execute, see, we have this expression. So the meaning is that you can see here x is 2 times and y is 3 times, and the total order of this partial derivative is 5. 2 with respect to x and 3 with respect to y. Okay. So further, if you need to compute this expression, what you will do, you will take more shell here and then use exp and do it. exp underscore partial dot do it function. So this do it function will do simplifying of the partial derivative, and when you will click on it, you can see at this place and at this place both have same value. So either you can use this way to take the partial derivative of the expression, or you can use this one also. So by using these expressions, we can easily calculate the partial derivative. Okay. So here we can have some more examples. Mixed partial derivative or function domain. Okay. So in the example number 6, mixed partial derivative, we have already discussed in the above, and if you need one more time, we can do by using the same expression, partial derivative. Okay. So here I am taking expr I am taking the same expression. Okay. And here if you need the mixed partial derivative, execute this one. Okay, add one more shell. So here exp underscore partial mixed, okay, is equal to, you can write here, and we can enter these values x 3 time and y 2 time. Okay, y comma 2 time, and when you will execute, see what happen. Yeah, so x is 3 time and y is 2 time, you can see. And after that, if you want to solve, then we can use here exp, then underscore partial underscore mixed dot do it. So we are using here do it function. We are using here do it function for further operation. Okay, so here this will compute, and we need to print the value also. So here exp, then underscore partial mixed, we can execute this shell. We are using here do it function, and if I will run from this place, yes, you can see this is the partial derivative of the expression. Sometimes if we have the function and we want to take the derivative, for that you can see the here, suppose that we have f is equal to some function. Okay, here f is function, then expression we have is, then expression we are using is equal to fx. X is the variable and f is the function. And diff underscore expr is equal to diff function we are using for the function, and we store the expression inside expression comma x. Okay, then we need to print the expression function, derivative of the function, and when you will execute, see this is the derivative of fx. So in this way we can use this one. And this again, if we have the chain rule, the chain rule is nothing but have the same way to take the derivative for the composite function. Okay, and suppose that here this is the chain rule. If you want to write this function, okay, f is a function of x square plus 3x. We can write here expression, and the syntax for the above function we have is x sine x square plus 3x, and when you will execute, this will print here. And if you want to take the derivative, we have the same way, take the derivative, right? Take the derivative. So the derivative is, we have 2x plus 3 cos x square plus 3x. So this is the derivative of this function. And sometimes if you have the implicit function x square plus y square is equal to 25, so how we can solve this type of the implicit function and how we can do? So we know here x is the variable and y is function of x. Okay, so here we will use from SymPy import. Okay, then x is equal to symbols. Okay, and then y is equal to symbols. We have the function y is the function. Okay, y is the function of x. We will write it as in this form, and then we can write the expression of the equation. Okay, so the equation, this we need to write this equation. Okay, so this equation can be written as eq is equal to eq is inbuilt function to write the equation. Okay, so this is the function, and on the left hand side we have x square plus y square, and is equal to 25. This is the way to write the equation. So the for the equation, left side is x square plus y square, and the right hand side will be after comma 25. Okay, and then after we can eq. When you will execute, symbols function this is extra bracket. Yes, now it's okay. So here now it is okay. We have the same x square y square, but y is function of x. Okay, is equal to 25. Now we can differentiate both sides separately. Okay, so for that what we can do, for the left hand side derivative is equal to equation diff, then we have the equation eq dot left hand side comma x. Okay, and then right hand side diff, okay, is equal to, we have this one. So we need to execute this statement. So the first equation is for the left hand side derivative, and the second one is the right hand derivative. Execute this statement, and then after recreate the equations. We have to recreate the equations. Okay, this is the way to solve the implicit differentiation. So here we will write eq underscore diff, okay, then is equal to eq, and in the side of bracket we will put the left hand side diff, comma right hand side diff. Okay, and then we will use here print equation, okay, and execute this one. Execute this one, and you can see we have this expression. Okay, and after that we have to solve the differential equation. Solve the differential equation. Okay, and then we have dy dx is equal to solve function is there, and then inside we will write here eq underscore diff, comma y dot diff with respect to x. So we have to solve the differential equation which is above, and then you can see, and the value will be dy dx, okay, dy dx. Minus x upon y. So this will be the value of dy upon dx from this expression, minus x upon yx. Okay. Then we have one more example for the parametric function. If we can have any parametric function, then how we can do? We have x is equal to sine t and y is equal to cos t, and we need the partial derivative of this one. So first we will write for the parameter symbol t is equal to, we have is a symbol, we have is t. Okay, then x is equal to sin t, and y is equal to cos t, and then dy upon dx is equal to diff we can use y comma t, and divide it by diff x comma t. So this will return us dy upon dx. So what I have done at this place, first I need to declare the parameter which is t. Okay, here symbols. Now it is fine, and x is equal to sin t, y is equal to cos t. Execute it. Okay, no error, but we need to print also. So this will be dy underscore dx. Again execute, and this is the derivative of this parametric equation. Okay, dy upon dx. And here is one more interesting example, and we will discuss. This is the last one. Okay, use derivative function. In the derivative function, we have already used this function, but once again, in this last example, we will do. Suppose that here is the expression. Write the given function. Okay. Then expression is equal to, we have is sin x square plus y square. Execute this one. Yeah. Here you can see sin square t cos x. Okay. So the thing is that here at this place the value of x is equal to sin t and y is equal to cos t. These are being considered at this place. So what I will do, I will update this one. I will take it as this is in uppercase, and this is also in uppercase. Okay, now see. Okay, the uppercase variables are not exist here, so we are not able to use it. So what I'm doing, use x and y only. Okay, no issue. And we will do this expression at the top. Just after this place. Okay, so I am adding a new shell here, and then I will perform the same. Yes, so execute this one. Yeah, add one more cell. So here we are using exp pd is equal to, we are using here derivative function. Okay, we are using derivative function, and here I am using expression comma x comma y. What if I am using the single, and then exp underscore pd, right? Check it. So the meaning is that if you are using the derivative function, we can return in the symbolic form. As you can see here, this is the partial derivative with respect to x of this function. If you are using here comma y, then you can see curl upon curl y sin x square plus y square. If you have the second order derivative, if you have third order, you can see this is the third order partiality with respect to y. If you are taking here x at its place, then this is the third order partiality with respect to x. Sometimes if we need the mixed partiality of any order, then y comma 4, okay, c. So in this way you can easily manipulate all these orders. But if you have write your code and the symbolic form is written on your file, then we need some more operation on it. We need to use here do it function. I am taking one more shell here. Okay, so use dot do it function, which is inbuilt function in the Python for further calculation. Okay, so this will calculate the further value. So exp underscore pd dot do it, and when I will execute, and you will see that this is the partial derivative of this function, and this is the partial derivative of a seventh order, third order with respect to x, and fourth order with respect to y. So in this way we can use this Python library SymPy for the different type of the order derivative and partial derivative, higher order derivative, for all type of the equations or the functions. So I hope that the discussion which we do at the place of how we can write the function in this Jupyter file, and then after how we can use the functions which are inbuilt in the side of the SymPy library, and we can directly import them, and only diff function is there, which is used for ODE and partial derivative both of any order. Okay, so I hope that this lecture will help you to understand how we can use all these expressions for the derivative. And in the next lecture we will discuss about the integration, definite and indefinite. Thank you to see this lecture till the end, and if this lecture is interested for you, you must share with your friends, with your colleagues,